Kia ora and welcome. This is the first of a mini-series of 4 webinars to showcase some of the recent developments in remote sensing technologies and how these are applied to answer questions for policymakers and councils and landowners. Manaaki Whenua lead the research and development of remote sensing of the terrestrial environment in New Zealand, and our research teams are at the forefront of developing and implementing cutting-edge technologies and methods to monitor and better understand the environment. This first webinar, Remote Sensing 101, will set the scene, and David Pairman will cover the basic concepts of remote sensing, various technologies used to create images, and analysis techniques which enable us to deliver valuable information. David has worked in this space, in inverted commas, space, for over 25 years and has first-hand knowledge of the rapid development of remote sensing services and what can be done with the data. I'll be back at the end of the presentation to manage our Q&A session. Don't forget to put your questions in the chat box as soon as you can. But now I'm handing right over to David.
Good morning, my name's David Pairman, and for the next 20-25 minutes I'll be giving you a very basic introduction to remote sensing, as Christine has said. Now, remote sensing has been around for a long time, many decades now, in fact my whole career, so it's actually more than 25 years, Christine, more like over 40. But in the past 10 to 15 years, it's really transformed from being just providing maybe amazing, stunning images of the Earth's surface to along with lots of research opportunities, and it's transformed into a much more operational usage, where nowadays we've been able to classify individual paddocks and get real critical information about our use of the land, its cover, and how we use the land. So this transformation has been brought about by an explosion in both the platforms that we use, that's the satellites in particular, and drones. The instrumentation's got a lot cheaper and smaller. Our computing facilities have got amazingly larger, and of course the analysis techniques are much more complex nowadays. So all of these things have made remote sensing a much more practical and affordable endeavour. So today I'll be just rushing through a number of concepts. First of all, a definition. I'll then talk about the concept of resolution, go through some of the technologies and instrumentation that are used in remote sensing, at least the main ones, and then talk about the platforms and their various advantages and disadvantages. And then I'll finish up talking about data processing and some of the techniques we use there. So starting off with a definition, remote sensing is all about acquiring information about an object without any physical contact. So it's an art and science of detecting and interpreting the emitted or reflected energy. We get reflected energy from the sun, electromagnetic radiation hitting the surface and coming back up to your instrument. We also get emitted radiation coming from the Earth's surface, and that's particularly energy in the thermal, microwave or gamma range that can be detected. And there's backscattered energy, where you actually send out a pulse of energy from your instrument and look at the reflected or backscattered energy, and that's the case for microwaves and LiDAR. So those are the basic modes of operation. I want to now talk about resolution, and there's 3 key types of resolution here. First of all, spatial resolution is probably what comes to mind when I say resolution. And this is all about how much detail we can see in objects. So high spatial resolution images, you can see a lot of detail. If you're looking at the same scales and lower spatial resolution images, then it starts to pixelate and you're not seeing that detail. But you really need to match your resolution that you're using to the objectives of your application. It's not always useful to have higher spatial resolution. For example, here we have a NOAA AVHRR image, 1 kilometre resolution. It's really good for looking at weather patterns, which is what it was designed for, maybe sea surface temperature patterns, and also probably broad patterns within the land, looking at perhaps droughts over a whole region, but it's not going to cut the mustard if you need to look at individual paddocks and determine what's in them. In that case, you need to move to higher resolution imagery, somewhere in the 5 to 30 meter resolution, provided by Spot, Sentinel, Landsat, those types of satellites or aircraft imagery. On the other hand, if you need much higher resolution, if you're looking at individual trees, perhaps trying to count stock, look at infrastructure, look at buildings, those sorts of things, you need very detailed information. You're probably looking under 1 meter resolution, and you're probably looking at either high resolution satellites or aircraft or drone imagery for those applications. I'll move on now to talk about the next type of resolution, which is spectral resolution. We're used to looking at the Earth through our eyes and the visible spectrum, blue, green, and red, but there's a lot of information available in other parts of the spectrum, going in both directions, but mainly out into the near infrared, mid infrared, and right out to the microwave spectrum. So resolution, the concept of spectral resolution is how well can we represent the returns from all parts of the spectrum, and it's really down to the number and placement of bands that we have available to us from a particular instrument. The final type of resolution I want to talk about is temporal resolution, and this is the concept of how often you can look at the same point on the Earth from an instrument or maybe an identical set of instruments. Why do we want to do this? Well, obviously it helps us avoid any data dropouts due to cloud or other problems, but it also helps us capture short-lived phenomena. So if we have a flooding event or perhaps an oil spill, then having high temporal resolution is going to help us capture those phenomena. There's other things like phenology and vegetation, so you might have a flowering event or senescence of a crop, and again, high temporal resolution helps you capture those events. I'll move on now to talk about some of the technologies, and the most familiar of these will be the optical technologies. This is your basic camera, which your cameras will be operating in the blue, green, red parts of the visible spectrum. But when we're talking about remote sensing, we're usually talking about not just the visible spectrum, but going out into the near infrared and even the mid and far infrared parts of the spectrum. So optical imagery is really a response to the surface color. We're talking about vegetation pigments if we're looking at vegetation, but also mineralization if we're talking about bare surfaces, rocks or bare ground. Gives us information about the types of rocks or bare ground from those spectral signatures. The advantages of optical, very high resolutions in general can be achieved, and they're very commonly used in the majority of remote sensing applications. For land care, of course, we're focused a wee bit more on vegetation, and we use it for classification, change, and also the health of vegetation can be observed through optical sensors. One branch of optical sensing is known as hyperspectral, and in this case, we're not just using a small number of spectral bands, but a very large number, perhaps 100 or 200 spectral bands, very narrow spectral bands, 5 to 10 nanometer bands, and the objective is to get a full spectrograph of the reflected energy, which gives us a lot of information about the targets. The processing of this type of information is a little bit different. We approach it from a spectral cube as a spectral cube and process it in that way. I won't go into the details of that, but it does allow you to do some tricks like spectral unmixing, which allows you to look at individual pixels which maybe have a mixture of targets within them. If you know a bit about the targets and you've got all this deep spectral information, you can actually unmix to some extent the proportions of those targets. The main use traditionally has been in the geology area, where you get different types of mineralization having very specific signatures in the spectrum, and you can determine that from hyperspectral imagery. But there's also applications in ecology, obviously looking at detailed species differentiation, and also plant health and coastal studies use hyperspectral. I'll move on now to talk about radar. This is an active technology where we send out a pulse of radar energy to the target, and it interacts with the target and gets scattered back to the sensor here. Usually on any one platform, it would be a single frequency radar, but different frequencies are used, and I'm showing two examples here, one from Sentinel-1 using shorter wavelength C-band, and another one from ALOS Pulsar using longer wavelength L-band. Despite it being a single frequency, these instruments are nearly always polarized both at their transmit and receive end, which does allow us to colorize the imagery from the actual effect on the polarization, and that tells us a lot about the scattering mechanisms and therefore about the actual targets on the ground that we're looking at. Unlike optical imagery, where you're basically responding to the surface color and pigmentation of leaves and that sort of thing, radar is more responding to scattering elements, and so you're looking at the size of the scattering elements, the number of scattering elements, their shape and orientation. And when I talk about scattering elements, I mean things that are similar in size to the wavelength that you're interested in. So, or wavelength that you're using. So if you're using shorter wavelengths, you'll probably be responding to leaves at the top of the canopy. Longer wavelengths will go deeper into the canopies and be looking at branches and even trunks. Other important aspects influencing the radar backscatter are the target moisture, and also surface roughness has a very specific scattering mechanism. One of the big advantages of radar is that it can see through clouds, and that gives you a regular coverage and makes it very useful for change detection. Also particularly used in related to biomass measurement, unlike optical where you're looking at colors. If you're looking at the actual scattering elements, as I've mentioned, that's more directly related to the biomass of the vegetation. So it's quite useful in these sorts of studies. There's a number of other applications for radar data. I won't go through them all, but maybe this final one, oil spills. That's where oil is on the surface of the water, and it tends to reduce the roughness of the water or the waves. And because of this effect on scattering from being affected by roughness, you can see dark patches on the water where the oil has spilt. The final technology I want to cover is LiDAR, and this again is an optical sensor where you're sending down an active pulse of active laser pulse from the instrument, which hits the ground, gets reflected, and it's the time of flight of that laser pulse to the ground and back again that allows you to build up terrain models and canopy height models and surface models. So there's heaps of applications for this type of data, in particular surveying and construction, hydrology, looking at buildings, but also vegetation, height and structure. As I mentioned, you're getting reflectance back from the laser pulse, and if you look at both the first reflectance from a pulse and the last reflectance, you can look at the top of the canopy and the bottom of the canopy, and many instruments will also give you returns in between those extremes, so you can actually get the full picture of the vegetation structure through the canopy. There's other applications, forestry, archaeology even, but I finally want to mention that we often use digital terrain models to correct other types of remote sensing data. Quite important to use those models for corrections. I'll move on now to quickly talk about some of the platforms that we mount these instruments on, starting off with satellites, which host a number of different types of instruments that I've talked about. The advantage of satellites is large regular coverage, so they're continuously deployed out there in an orbit, and that in many cases they're actually continuously collecting data. So that makes it cheap-ish data. Even the commercial satellites are probably cheap on a per kilometre squared basis compared to other platforms. However, it's not cheap to put a satellite up, so the instrumentation tends to be of very high quality and well calibrated. And that's a real advantage because it makes it easier to standardize that imagery for later processing. The disadvantages tend to be a little bit limited in their temporal resolution, limited by the orbits that they're in. You might only get a pass every few days or weeks, and that can be ameliorated to some extent by putting up constellations of identical satellites. There's also tend to be a bit limited in their spatial resolution. There were regulations around this in the past. I think they've been relaxed a little bit nowadays, but even now you're still not going to get the very highest resolutions out of satellites. Moving on to talk about aircraft here, this is probably the traditional remote sensing platform from the dawn of the aerial surveying, probably 100 years or more ago. So aircraft can be anything from fixed wing, helicopter, or even very large aircraft like this NASA DC-8 that came with a lot of radar experiments. You can see the radar panels on the side. That was brought to New Zealand back in 2000. So the advantages are that, you know, they're a little bit more flexible in their deployment than a satellite. You can get the very high resolutions, and you can put experimental instrumentation onto an aircraft more easily than you could onto a satellite, or go through the issues of miniaturizing it for a drone. The disadvantages, of course, there's a number of them listed here, but the one I'll focus on here is the difficulties in calibrating imagery. Usually they're smaller footprint images, and they're looking out at wider look angles to the Earth below them. So that just makes it more complex and more time consuming to adequately calibrate and pull the images together into seamless mosaics for later processing than it would be for satellite imagery, for instance. I'll move on to drones, and this can be anything from toys that you could buy at a toy store right through to large military drones, which are probably carrying more than just a remote sensing instrumentation. But they do carry the full range of remote sensing technologies, and their advantages are very high resolution. You can fly drones low, you can fly them quite slow, you can tailor their deployment. So they're really ideal for certain applications. If you have a limited extent, perhaps you have a farm or a vineyard that you want to cover on a regular basis, and you could probably afford to set up a drone and run it just for that single purpose. They're also used a little bit in relating different scales of remote sensing. So you can use drones to actually pick up ground truth for wider scale studies, such as a satellite-based study. Might be useful to get some drone imagery close to the ground. And conversely, you can use it to relate field work up to the above canopy view. So if somebody's working in a forest measuring plants and whatnot, you might want to use drones to see what that would look like from above, which is quite useful. The disadvantage, of course, is the small coverage extent, and at the moment the regulations to a large extent require line of sight operation, which is a big limitation. These regulations will probably, I'm expecting, will probably relax over the next decade or two, and I can see when that happens, drones eating into that aircraft-based remote sensing domain to do regular surveys, as satellites already do from the other low-resolution side. So it'll be quite interesting to see what happens over the next few decades in the types of platforms that are mostly used for remote sensing. I want to finish off really talking about data preparation and processing. There's a lot of things that we can do to data to, I would say, pre-processing steps before you get into any particular application processing. And this is things like calibration, the instrument atmosphere where required, Rectification is very important, so relating points in the image to a particular map projection, like the New Zealand transverse Mercator projection, allows it to be used directly with other imagery taken at other times, but also other imagery from other platforms or non-remote sensing imagery. So all these things need to be done before you can use the images in an application sense. And another one is the standardization of the radiometric effect, and this is both applies to optical and radar. You can see here on the left we have reflectance varying quite a bit just due to the terrain that it's on. So you've got vegetation that's probably similar vegetation, but it's looking quite different depending on what facet of the surface is actually on, and standardizing that as we have done on the right by modeling this bidirectional reflectance effects helps to then process this data at the later step. So if you have an application where you're trying to classify the actual vegetation, it would be much easier to do it where you've taken out those terrain effects. So all these things are pre-processing steps. Obviously, identifying any bad or corrupt data is important also. Now I'll move on to talk about the analysis techniques used, and I guess the simplest and most obvious is just a straight manual interpretation. This is sitting in front of a screen and identifying features in the image or boundaries, objects in the image, and humans are very good at this. We can use our context and use the context of the image and our experience, and even if I show you this black and white image, I'm sure that you can recognize trees, cars, roads, buses, buildings, etc. with no problem. Those of you that know the area could probably even tell me that that is Christchurch Cathedral Square pre-earthquake. So we bring a wealth of experience and are very good at looking at images at different scales simultaneously. You're not going to get confused by some of the detail in the buildings. You can still see that as a whole building quite easily. So humans are very good at interpreting imagery, but it's certainly labor intensive and will very quickly be overwhelmed by the quantities of data that we have coming from remote sensing platforms. And the other thing I should note is that it's actually quite difficult to visualize some aspects of remotely sensed data. If you've got more than 3 bands, for instance, it's very difficult to visualize multiple bands simultaneously. And similarly, if you've got a lot of temporal steps in your imagery, it's difficult to visualize that. So manual interpretation certainly has its limitations. I'll move on to talk about another type of analysis technique, which I would say is physics-based modeling. And this is appropriate where you have a really good understanding of the physics relating the data received by the instrument to the parameters that you are seeking. So things like surface temperature, it's well understood. You may have to do some atmospheric calibration, but the physics is pretty understood. I've already mentioned LiDAR, and there's other things like albedo might be used for global radiation budgets and that sort of thing, and wind speed, where you're looking at surface waves on water, can tell you things about the wind speed and wind direction just from the physics of the problem. So understanding that physics and inverting models is one approach to analysing remote sensing data. But by far the most important type of technique in remote sensing is data-driven techniques, and this has really taken over most remote sensing analysis over the years. And this is anything from the very simplest analysis right through to machine learning and deep learning techniques. So I'll start at the simple end. You could just basically represent using thresholds, say that a pixel that falls within a defined range and one or more of its features or bands will belong to a particular class. So you're just defining a few thresholds which you can tweak around until you're satisfied with the result. A more statistical approach might be to define a mean for each of the classes that you're trying to classify, and say that a new pixel coming along belongs to the class that has the closest mean. take that one step further, you could represent each class by a multivariate normal distribution, in which case you need not only the mean, but a covariance matrix for each class. And so these are all constrained models, statistical models, ways of looking at data, but they also have limitations. If you take that last case I mentioned, a multivariate mean, you're making assumptions here that the underlying class also does basically have a normal distribution. And if it doesn't, you're not going to get good results. So if, for instance, the underlying distribution of your class is very skewed or bimodal, then it's simply not going to work well. And you may need to look at splitting that class up and to get adequate results. So what I'm really saying is that you need to be aware of the limitations of the model that you're using and how that relates to what you're actually trying to detect. Nowadays, we have a lot more modern techniques in machine learning, going through right through neural networks to deep learning techniques, and these are sophisticated techniques that are able to bring a lot more information to the decisions being made. The deep learning techniques don't just look at an individual pixel, but can make assessments about the context of surrounding pixels and whatnot. So that's a lot more information, and they can provide some fairly stunning results. But these types of approaches still have limitations in the types of problems that they can be classified, and it's not always obvious what those limitations are. When you're using, for instance, a neural network, you're passing information from one layer to the next and successively refining your classification. It's not obvious what the limitations of that classification actually are, and so you need to really rely a lot more on training and truth data. So these are training data hungry algorithms, unlike constrained statistical models. They need a lot of data to train on, and you also need a lot of data, truth data, that's independent from the training data to understand how well the algorithm is actually working. Both of these need to be well distributed over the range of inputs for any one class that you're trying to detect. You don't just want a few examples, but you want a range of examples that are well distributed. Now, there are strategies available for making best use of your training or truth data and partitioning that data set. Usually it's a fairly scarce resource, so you want to partition it and reuse it in different runs through the model. And there are other ways of transforming and perturbating the training data to try and leverage it even further than that. So there are tricks and techniques to do this, but I guess my point is that there are still underlying limitations, and you may have to actually look at going back and changing the architecture of the model, the number of layers used, or the functions that are used within each layer in order to get an adequate result for some particular classification problem. Now, Brent is going to talk a little bit more about some of these techniques tomorrow. I believe he's going to be talking about some shortcuts and training data and using imperfect data and that sort of thing. So I'll leave it here, and I've really run through some of the basics on remote sensing, and I'll open up for questions at this point. Thank you.
Kia ora, and thanks very much, David. That was really fascinating, and I didn't jump in and cut that off at the end to leave time for questions because I was so gripped by what you were saying. But we have got some questions, and but we're also out of time. I want to reassure everyone that's asked a question that we will come back to you, and we will also publish all the questions and answers on our website once we've collated that all together. So give us a few days, and some of that information will be forthcoming. Just a quick reminder, as well as Brent's presentation tomorrow, Stella is talking to us this afternoon about winter forage crop mapping, which is a great application of many of the things that we've been talking about today. So I'd like to say a big thank you to everyone for coming along, and maybe we'll see you again this afternoon. And a huge thank you to David. That was great.
Okay, thank you. My apologies for running over a little bit, a lot.
We were enjoying it.
Thank you.